Let's look at chapter 4. Now, chapter 3, remember, was on stoichiometry, which is a way of tracking reactants to products, so we can predict what we should expect from a reaction. And our examples were only weight-based. In other words, we started out with so many grams of this reactant and that reactant, end up with so many grams of the other. At the end of this chapter, we're going to look at stoichiometry in terms of solutions. But first, we need to get a handle on types of chemical reactions. We're going to focus our attention for solutions here on aqueous solutions. In other words, the solvent is water. Just for several reasons, but one of the main ones is there's not enough time to cover all types of solutions. I mean, we know anything can be a solution if it's a homogeneous mixture, but we're going to focus on water. And there's one characteristic of water that makes it, they used to say universal solvent, but I quickly discovered that that was a lie. Water cannot dissolve everything. It dissolves a lot of stuff, but not everything. And one of the reasons that it dissolves things is its shape. Well, two things. Its shape, there's oxygen, and here are your hydrogens. No, it's already dead. Here are your hydrogens. All right. And there's a thing called polarity. In other words, oxygen has a stronger pull on the electrons in that bond than hydrogen does. It's called electronegativity. So oxygen is pulling electrons that direction. Now, it doesn't pull them hard enough to break the bond. Not like an ionic compound where the electrons are transferred completely over here. They're still in that bond, but they just spend more time over here. And same for this one. So what that does is it gives oxygen a slightly negative charge. It's not a full charge. That's why I use that little delta. That means slight. And that means this side of the molecule has slightly positive charge. So whenever they encounter one another, if this is a pure solution, when they encounter one another, there's an attraction. Say another water molecule happens by, right? There's an attraction between those two. And that's why water is a liquid at room temperature and pressure and not a gas. If it were not for this fact, then we'd be in big trouble, because we wouldn't have any liquid water on the surface of the earth. Okay, so that's pure water. Suppose you put something in there that also has either a charge or a partial charge. Like if we put sodium chloride in solution, what it does is it breaks up into ions, right? Sodium ions and chloride ions. Well, which side of the molecule is going to be attracted to this one? That side. Which one's attracted to this one? That side. So they go through a process called hydration, and the chlorides get surrounded by water molecules from this side against the chloride. And water molecules surround the sodium this side around the sodium. And those are ionic compounds. If you have a similar situation for, say, you have a polar bond in a molecule, then it will also associate, like, let's pick ethanol. You know, the drinking kind. It's got an alcohol group there. That means this bond is going to be polar in that direction. So it's going to be minus there and plus there. Well, which side is attracted? If you put ethanol in water, you know it's going into solution very easily. So you're going to get attractions here between this one and that one, and this side with that one. And that's what keeps it in solution, those attractive forces. Oops, I think I have to start it manually. Oh, there's no narration in this one. Just as well, it's a Canadian product. They'd probably be talking in French anyway. So that's supposed to be a water molecule. Shows that the molecule is polar. And there's your sodium chloride. And in the crystalline form, you've got your sodium, your chloride blues and your sodium reds. And the attraction is between positive and negative. And the water molecules that can associate themselves with the positives or the negatives expose on their backside the opposite charge, and other water molecules come in and start pulling on them. And the force of that attraction is enough to dislodge those ions from the crystal. And of course, once they're pulled free from the crystal, you got other water molecules that surround them. And eventually you get sodium ions and chloride ions in solution. Well, there's a maximum, right? You reach a maximum solubility, we say, where you can't put any more sodium chloride in solution, right? It's saturated. It's a very high value, right? Very large amount, but it still is, it happens. Okay, so when we're talking about these solutions, these homogeneous mixtures, our terminology is such that the major component is the solvent. And in our previous discussion, that would be water. And the minor component is the solute. Now, you can only have one solvent, but you can have many solutes. So in this case, the solute would be sodium chloride, but it could be anything. Or we could put sodium chloride in there, and then we could put table sugar in there, and then we could put alcohol in there, have a whole bunch of different solutes, but this is still the solvent. Another term that's often used is electrolyte. And this is more an operationally defined substance. In other words, an electrolyte is anything that you put in water that dissolves in water that will also conduct electricity. Pure water is an insulator. It takes an extremely high voltage to get any current to go through water. Now, if you're bathing in the tub and talking on the landline, and along comes a thunderstorm, strikes the telephone line, comes down straight through you and through the water, well, the voltage is high enough that it will ionize the water. Plus, you've got ions in your body that conduct. So that's another story. But low voltages are not conducted through water. You need something in there to carry the current through from one electrode to the other. And those are electrolytes. Anything that will allow water to conduct electricity as a solute is an electrolyte. Now, when you get your blood work back or your urinalysis back, and they have this list of positive and negative charge things in there, those are your electrolytes. Right? They'll list sodium and potassium, magnesium, calcium, chlorides, some others, depending on what the doctor wants to see. But those are electrolytes, and they're charged species. Now, if the electrolyte allows a large amount of current to be conducted through the water very efficiently. And if you put a light bulb in the circuit, you'll see the light bulb be very bright. Those are strong electrolytes. So sodium chloride would be a strong electrolyte because it completely dissociates in water. Or strong acids like hydrochloric acid or sulfuric acid or nitric acid. Those would be strong electrolytes. They just completely dissociate and give lots of mobile charges. Weak electrolytes are those that only slightly dissociate, like weak acids. Acetic acid would be an example. And if you have a light bulb in the circuit, it'd only be dimly lit. Non-electrolytes are those that will go into solution and they do not conduct electricity because they don't break up into ions, like glucose or sucrose, sugars like that. They will readily go into solution, but they don't break up into ions, so they can't convey current through the solution. Those are non-electrolytes.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
Okay, so she made a good point that I missed. When you have an ionic solid, those ions are locked in place. They cannot move. So they are insulators. All ionic solids are insulators. If you can get them into a solution where you can separate the ions, then they will conduct electricity. So two ways to do that is put them in a solution like this or melt them. If you melt them, then the ions can move. Okay. These chemical reactions, in order to characterize a chemical reaction of solution, we need to know what's the nature of the reaction, what type of reaction it is, and we're going to talk about that in a minute. And then we need to know the amount of the reactants that are available in the solution. That is, if we have a very dilute solution, not very many of the reactants are in solution, then you will get either a slow reaction or a very weak reaction producing very little product. So we need to know those two things. What type of reaction is it? How concentrated are the reactants in solution? To that end, we need a way to express concentration because these are mixtures, and mixtures can have variable composition. In other words, we can have a lot of salt in solution, we can have very little salt in solution. But an expression of the concentration is what we're after. And one very useful expression of concentration is molarity. Molarity doesn't ignore the existence of different components. It just sets them aside for now. We can use the whatever it is later, like it's sodium chloride or it's phosphoric acid or whatever component. If we say molarity, we're saying so many moles of the solute dissolved in a liter of the solution. So that solute could be anything. If we just say 3 molar and don't put anything behind it, we know that there are 3 moles of something per liter. But until we identify what it is, we can't say anything about its potential as a reactant. So 3 molar hydrochloric acid One way to create that solution is put 6 moles of hydrogen chloride in 2 liters of solution, right? It's an equation. Molarity equals, okay, my abbreviation for moles is N divided by volume. And by definition, this volume has to be liters. And these, of course, are moles. So if we have 500-gram sample of potassium phosphate and we dissolve it in water and we produce as an end product 1.5 liters, remember this is volume of solution. That includes whatever effect the solute has plus the volume of the solvent. So this is a final measurement after we dissolve in solution. So if we have 500 grams of potassium phosphate, let's get it on here. 500 grams potassium phosphate. What's potassium? K, right? The phosphate is a polyatomic ion. It's PO4 with a 3- charge. This is an alkali metal, so it has a +1 charge, always and forever in a compound. So in order to balance these, we need 3 of these positives, right? And that will balance the charge. So that's your formula. You got to be able to do that. Otherwise, these word problems are going to stump you. Dissolving enough to make, and the volume now is 1.50 liters. Okay, so we can't go straight from here to here because that's not moles. We got to convert that to moles. All right, so how do we do that? Dimensional analysis. If we have that many grams, we need a conversion factor that will cancel grams and leave us with moles. And whenever you see grams and moles in a quotient relationship, think molar mass. So what's the molar mass of this compound? Well, potassium is 39.10 to 2 decimal places times 3, right? We've got 3 of them. 1 phosphorus, 3097. We got 4 oxygens, 16. We add those together. I think I've already got it calculated here. There it is. 212.27. 212.27 per mole. Right? So all I have to do is divide this in to that, and that'll give me the number of moles, 2.355. Now that we have moles of potassium phosphate and a final volume, we can set up the calculation, 2.355 moles per 1.5 liters. And that will give us a calculation of molarity for this solution, 1.57 molar. Okay? That's how it's done. Now again, this is an equation, right? Molarity equals moles per volume, liter. So if we know 2 of those, we can solve the 3rd one. If we already know what the molarity is, and say we have 300 milliliters, that's 0.3 liters. Then 0.3 liters comes over here times that, and that gives us the number of moles. So we can, it's like any equation. If you only have one unknown left, you solve for it. Okay. Now, when we put these things in solution, what do we get from that? I mean, this is another example, but I'm going to go from here. When this goes into solution, what do you have? You have 3 potassium ions and 1 phosphate ion. Right? So you actually are creating 4 ions out of this solution. So what is the concentration of the potassium ions? It's 3 times that value. What was it? I forgot. 1.57. 1.57 molar. So the concentration of this is times 1.57 molar, or about, oh, I don't know, 4.6 or 4.7, something like that, molar ions. Now, why would we want to know that? Well, at pure chemistry, we need to know what the concentration of the ion is, because that's what reacts. It isn't the molar amount here that reacts. Once you get in a solution, these are the reactants, not that. The other is very practical and life-threatening problem. If you mix up an isotonic solution, everybody know what isotonic means? It's the same concentration of electrolytes, of solutes in the solution that is in your body fluids. So if you get an IV with an isotonic solution, it won't destroy your blood cells. That's the first thing to encounter, right? If it's hypotonic, then it'll cause your blood cells to go like that, just crenate. If it's hypotonic, it'll cause your blood cells to go boom, like that, and the patient's dead. So, and it's based upon the concentration of these things, not that thing. So that's why we want to know the ionic concentration. In fact, the total concentration would actually be 1 plus 3 is 4 times that. It'd be to 6.5, maybe, something like that. I don't know. I'm just estimating. Okay, so with our example here, 0.25 molar calcium chloride produces 1 calcium and 2 chlorides. So the calcium concentration is the same as the original, because the ratio, like this one, is 1 to 1. For every one of these, you get one of those. So its concentration would be the same, 1.57 here. The chloride, but would be twice the concentration. Be 0.5 molar chloride. Okay, which of the following solutions has the greatest number of ions? This requires you to think in terms of, first, concentration times volume times molarity is the number of moles. Greatest number of is moles. So M times V equals the number of moles. And then, since we're talking about ions, we want to know, how does the solute react once we put it in solution? Sodium chloride makes 2 ions. Calcium chloride makes 3. Iron 3 chloride makes 4 ions. Sucrose makes none. All right. So this is where we would need to use Henry Ford, set up an assembly line. So I would say A, B, C, and D, and 4, 3, 2, and 8. Milliliters, correct? Yep, milliliters. Okay. And the concentration of each one is 0.1 molar. I'm going to show you a trick here in a minute. This one is sodium chloride. And I should have remembered this. Calcium chloride and iron 3 chloride. And this is sucrose. All right, since we're talking about the number of ions, we don't have to bother with that one. It doesn't make ions. Now, the rest of them, we can do it in steps. We can say, how many moles of the compound do we have? And then we can take that value and go to ions. Or we can do a straight through calculation of a multi-step calculation. One thing, this saves you the trouble. Now, in reality, the calculation of molarity is based upon moles per liter. But if we multiply 400 times 0.1, we get 40. Right? 40 millimoles. Milliliters times molarity is millimoles. Now, does anybody not believe me? I'll back calculate. Okay. So let's say we have 40 millimoles divided by what volume? Total volume of 400 milliliters, correct? Right. Millimoles per milliliter. Well, the millis are going to cancel, right? That's 1,000th of. Cancel the millis. Now we have moles per liter. And that gives us 0.1. So it just saves trouble. And if we're only going to do a comparison, right? Millimoles is just as good as moles. So this one would be 30 millimoles, and this one would be 20 millimoles. This is of the compound. Okay. Now we want to convert to ions. So what we need is a conversion factor that goes from compound to ions. What's the ratio in each case? For every one of these, we have 2 ions. So 2 moles of ions per every 1 mole of compound, or 2 millimoles of ions per millimole of compound. This one has a 3-to-1 ratio, and this one has a 4-to-1 ratio. So now if we multiply 2 times that, we get 80 millimoles of ions. And this one we get 3 times 30 is 90 millimoles. And this one we get 80. So which one makes the most ions? Calcium chloride in this problem. Okay. Silence. Moving on. It'll make more sense if you work a few of the sample problems in the handout. Okay, here we are again. What's the question? How do we get there? Check yourself on the end. The moral of this story is the solution with the greatest number of ions is not necessarily the one with the largest volume. It has to do with the volume and the species. Okay, here's a practical problem. We used to do soil tests, which very often were the result of extractions. We'd use various types of solutions to extract nutrients from the soil and then analyze them. But the solutions were usually fairly dilute. They needed to be to give us an accurate estimate of what was available to the plants. So the solutions, rather than making up the dilute solutions every day when we were going to run 200 or 300 samples, we would mix up a concentrated solution in usually a big carboy, and then we take out a certain amount of it and dilute it with more solvent, and that would make it ready for extraction. Well, this is the formula, and I'll show you why it works. Yep. Well, as soon as I get a marker that works. So instead of M1, V1, M2, V2, let's use concentrated, dilute, dilute. So why does that work? Let's see if I've got an animation here. Okay. Let's draw a picture. See, I've got my big vat of concentrated solution. This is and it's at a concentration there of some molarity. Okay. And then I want to dilute it over here in a volumetric flask, which is calibrated to be, let's make it easy on ourselves, exactly 1 liter. So the volume, that's the volume of the dilute. The diluted solution is going to be 1 liter. Now, if I want to reduce the concentration of this one to that one, I only need to take part of it out. So let's say I take out a volume of my concentrated solution here, and I transfer it over here, right? And then I fill it up with solvent. Okay, we know intuitively that it's going to be more dilute now. But if I take this concentration and that volume out there, what am I actually transferring? I'm transferring solute. And the solute amount is that, right? Because this equals that over that, and this equals that. So if I say M times V, I'm equal, that's the number of moles from the concentrated source of the solute. Okay. Well, does this change when I bring it over here like that? No. The moles that I add here are exactly the same, right? I didn't change anything unless I spilled some. Right, let's assume I'm perfect and I didn't spill any. Okay, what's that equal to? Well, now that it's NV, it's over here, then that's equal to molarity times volume, right? Well, what's that cumulative law in math? If A equals B and B equals C, then A equals C. So if this one equals that, and that one equals that, then this one equals that one. Okay? So now we've got a formula, and all we have to know is 3 of those, and we can solve for the 4th one. So the way I was describing it earlier, when we were mixing up these diluted solutions, we knew this one right here. We knew what that had to be. And we knew this because we prepped it. All right. And we knew the final volume because we were going to dilute it to a certain volume. That means this is the unknown. So if I solve for that one, that tells me how much of this one needs to be drawn out and diluted. Okay. And if you do this for years on end, it's second nature. You don't even have to put it on paper. You just do it in your head. Okay. So that's what I'm saying right there. All right. Let's make this quick. 0.5 molar solution of sodium chloride is on an open beaker, sits on the lab bench. Which of the following would decrease the concentration of the salt solution? Right? Is the sodium chloride volatile? No. Whatever you got there stays there. What else is in that beaker? Water. Is water volatile? Yeah, to a certain extent, right? In an open beaker. So if we just sit it on the bench top and let it sit, is it going to become more concentration or less? Decrease the concentration, it's going to be more concentrated, right? So, but if we add more solvent to it, that will decrease the concentration. And that's section A. That will decrease the concentration. If you pour some of it down the sink, what are you doing? You're pouring solvent and solute of the same concentration down the sink. You're not changing the concentration at all. Add more sodium chloride, that will jack up the concentration. Let the solution sit on the bench, water evaporates, increase the concentration. And at least two, no. Just add water to the solution. That'll do it. All right. Elbow grease. All right. What is the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? Okay, when you have a word problem like this, it's best to extract the information into a form that makes sense, right? Because the number one rule of word problems is confuse. So, what's the minimum volume? So we're looking for the volume of the concentrated solution. How much concentrated do we bring out if the concentrated is at 2 molar? Okay, to make what volume of the diluted solution? 150 milliliters. And, oops. We want the diluted solution to be what concentration? 0.8 molar. Now that you've got your information up here like that, you're certain to get it in the right place in your formula. If you try to go straight from the word problem to the formula, you're liable to get them in the wrong place and get the wrong answer. But if you do like this, then you know you're going to put them in the right place. So if we have MCVC equals MDVD, and we solve for the one we want, this one, over MC. And notice this is a ratio. This ratio of volumes and molarities, we can leave this volume just like it is. Now, if we have the standalone formula like that, we have to use liters, no choice. But if we have ratios like this, we can use this same volume, and that means this volume is going to come out as milliliters. Okay, so we can plug in the numbers. MD 0.8. I'm going to leave the units out for now. Let's see, volume D 150 milliliters, and MC is 2. Okay. I think I've got it animated here. Here we go. Solve for unknown. Our answer comes out as 60 milliliters. So if we take 60 milliliters of a 2 molar solution and dilute it to a final volume of 150 milliliters, we will get a 0.8 molar solution of sodium hydroxide. Now, should we wear gloves when we're doing this? Yeah. Even the 0.8 molar will find any little cut you got on your hand. You'll feel it just like that. All right, now let's look at different types of reactions. This information is accumulated over the decades, centuries actually, for some of them. So what you'll find is when we identify a certain type of reaction, and the major types are those 3 at the top, and then other types below, you can have one reaction that fits in multiple categories. Okay, that's always possible. But the major categories are precipitation reactions, acid-base reactions, and oxidation reductions. Precipitations are ones that produce a solid. Put 2 solutions together, and remember I just went blank. The Tyndall effect says that you shine a light through that solution, you can't see the light being inside the solution. So this precipitation reaction is two solutions together and it forms a solid. Right? It gets cloudy. And if you wait long enough, it'll settle out on the bottom. Acid-base reactions, just that. You put an acid together with a base, what are you going to get? Oxidation reduction reactions require a transfer of electrons. So if electrons during the reaction are transferred from one species to another, then we have an oxidation reduction reaction. Now that reaction may also produce a precipitate. It's possible. Or it could be an acid-base reaction too. So you have those possibilities. Now, if we look at these other types, they're more operationally defined. A combination reaction is also called a synthesis, where you take two simpler substances and make a complex product. I've got slides on it, so let me not dwell on this. Decomposition is the opposite. You take a complex and you make simpler substances out of it. Single displacement, you have a binary compound and you have an element and it replaces one of those. Single replacement. Double replacement is you have two binaries and they swap dance partners, right? The cation goes to one and the cation from that one comes back over the other one. And then a combustion reaction is anything combined with oxygen is combustion. Okay. Let's see. We're taking these out of order, aren't we? Oh no, that's the first one. Precipitation reaction. Actually, a precipitation reaction is usually a double replacement reaction. So you've got a binary compound here and a binary compound here in solution, right? In solution. So there's cation, cation, anion, anion. And we just swap partners. So the A and the C swapped. So we get a C and a B, and an A and a D. And one, usually only one, but sometimes both, will produce a solid. Let's just say it's that one for argument's sake. Okay, that's a precipitation reaction. Now these can be elements or they can be polyatomic ions, but they're binary in nature. And the precipitate is what we call the solid that forms from this reaction. Now, when they dissolve in water, let's see if we've got an example. Yeah, here's an example. Barium nitrate is soluble. Potassium chromate is soluble. Put them together, what's going to happen? Well, the barium is now, well, in solution, you've got barium ions and nitrate ions. And the other solution, you have potassium ions and chromate ions. So when you put them together, now the cations from one have access to the anions from the other one. So barium combines with chromate to make barium chromate. It's a solid. It's not soluble. Whereas potassium from one combines with the nitrate of the other one, and it's perfectly soluble. So it stays in solution. And the product that drops out of solution as the precipitate is barium chromate. Oh, and here's another possibility, silver chloride. Silver nitrate and sodium chloride. I don't know which is which. Probably dropping silver nitrate into a sodium chloride solution. And it forms silver chloride, which is insoluble. There's another possibility. Silver thiocyanate. Well, actually, that doesn't last very long. It decomposes into silver sulfate. Barium and sulfur sulfate makes barium sulfate. Anybody ever had a barium enema? That's what they use, barium sulfate. Because it's insoluble. Right? Inside your colon, it will not absorb into your tissue. But barium is a massive atom. and it very effectively attenuates X-rays. So it gives a beautiful outline of your colon and any abnormalities that are there. It's almost like it's forming a gel. Okay, so much for that. And moving on. Come on. Force it. There we go. So, when we speak of precipitates, we're talking about an insoluble solid. Soluble solids are those that go right into solution. And we designate those as AQ, aqueous. If our solvent is water, we say it's aqueous. The precipitate is identified as a solid. Now, at this point in the course, we're going to make a distinction between soluble and insoluble, but recognize that this concept is on a continuum. Even insoluble solids are very slightly soluble. Not much, just very slightly. Second semester is when we get into actually calculating what that solubility is. But for now, it's either soluble or it isn't. And there's in this review document on the back, I've got a slide up. There's your solubility chart. Since you guys are not chemistry majors, I'm not going to make you memorize the rules. But the rules down here generate this chart. And to use the chart, which will be available on exams, you look at the anions here and the cations here. So when you put these two solutions together and you see that this cation now has access to those anions, do they react to form a precipitate? Well, you find the cation up here and you follow it down until you reach the anion. And if it's grayed out, yeah, it forms a precipitate. Okay. If it's not grayed out, then it stays in solution. Okay, there are the rules just for posterity's sake. And these rules are set up, if you ever encounter the rules again, the rules are set up so that if you have to break a tie between two rules are operating at the same time for a combination of two solutions, then the rule above takes precedence. Right? So that first one, nitrate salts are soluble. And for our purposes, I could say all nitrates are soluble. Most alkaline metals are soluble. Right? Most salts, chloride, bromide, iodide salts are soluble, except for silver, lead 2+, and mercury 1+. Remember, mercury is one of the weird ones. It's either like this or it's like this. It's always a 2+ charge. But if there's only one of them, that means the charge on that mercury is 2+. If there are two of them with that charge, then each mercury has a 1+ charge. Okay, that's the way you'll see them. Right, those are the rules that were used to generate this table. Right, the table is, there it is. We'll get to it in a minute. So which of the following ions, form compounds with lead 2+ that are generally soluble in water? The easy answer is all nitrates are soluble. So lead 2+ and NO3 will give you a soluble compound. And sodium was thrown in there as a ringer, right? Lead 2+ and sodium are not going to form a compound because they're the same charge. Okay. Now, when we write an equation for this type of reaction, right, where you have two solutions of ions, like for instance, sodium nitrate is going to break up into sodium ions and nitrate ions, sodium chloride into sodium and chloride ions. And then when you put them together, sodium has access to nitrate, silver has access to chloride. So you get sodium chloride as a product, which is insoluble, and sodium nitrate, which is still soluble. right? Because all nitrates are soluble. So this is known as the molecular equation, or actually formula equation is the accurate term. Molecular means that there's a covalent bond between the molecules and they act as a single unit. Whereas ionic compounds, we know don't do that. So formula equation is, but you'll see it both ways. So when we write them like this is fine for doing calculations. Silver nitrate and sodium chloride. Then silver chloride and sodium nitrate. Okay, that would be the molecular or the formula equation. But in reality, the complete ionic equation is next. We actually have to break these up into their ions. This is a +1 charge, that's a -1 charge. So we would write it silver plus, and that's an aqueous solution, nitrate minus in aqueous solution, sodium plus in aqueous solution, and chloride plus in minus in aqueous solution. And they come together, and we keep this one as a solid, right? Because it's dropping out of solution. And then you have sodium left over and nitrate left over. Still in solution. Okay, got the same number of moles here as here in that solution, and same here and here. Wait a minute, here and here. That's the complete ionic equation. This is reality. This is actually what's happening in the solution. But as a practical matter, what's driving this reaction? It's not these guys, it's these two forming that solid. Because what happens when we form that solid? Now these ions are removed from solution. Right? They're removed from reaction. They drop out. And we're going to learn later, I'll give you a hint, Le Chatelier's principle. When we remove these on that side, that drives the reaction to the right. So the formation of precipitate is one of the driving forces for some reactions. So silver and chloride, we want to keep those because they're essential to describing the reaction. This is the net ionic equation. This is what's making it happen. There's a practical reason for this also. And by the way, this is, and this one, these are called spectators because they're the same on both sides. Nitrate over there, nitrate here, sodium there. Those are spectators. If you're trying to set up a reaction in the lab and you find that, whoops, I don't have sodium chloride in my lab, which is kind of strange. All labs ought to have salt. I mean, you go to the kitchen and get salt. But for argument's sake, say we only have potassium chloride, right? We just substitute potassium in here. Right? We get the same net reaction. Okay, on a molar basis, exactly the same reaction, same outcome. Okay, so here's another example. Kind of running out of time, so I'm not going to stop on this one. But there it is for your interest. This is where I would normally pause. Now we're going to talk about stoichiometry of solutions. So we want to be able to start off with a certain amount of reactants in solutions. And then when we precipitate a reaction, and I shouldn't use that word because it's got a specific meaning now. When we make the reaction go, we can predict the outcome. Let's see. Everybody looked at the rest of last week's video to get fill in the picture where we left off? If you didn't, go back and read it or then look at it. Then this will make more sense. These are just step-by-steps. And this is that chart. So if we look at, let's see, where's silver? Silver is right here, right up there. Can you see that? Oops. Well, that I think gets in the way. Silver, and then you can run down to find either chloride, bromide, iodide, all three of those under silver are grayed out. So those halogens will, as ions in solution, will form precipitates with silver. All right, so let's take this example. Say we have, and look at it this way, we want to know the balanced equation first before we can determine a stoichiometry. So what we're seeing is sodium phosphate solution. Sodium phosphate. We got sodium and we got phosphate with a 3 minus and 1 plus. So that means this one has to have 3 to balance that charge. And this is solution. Right? Is reacting with what? Lead 2 nitrate. So that says that lead has a 2 plus charge. That's the Roman numeral says it does. And nitrate with a -1 charge. So that means we need 2 of those guys. Okay, when we put those together, what happens? Well, we have the potential for lead reacting with phosphate and sodium reacting with nitrate. So lead 2 plus reacting with phosphate 3 minus, and you look it up in your chart. Go back to your chart. Let's see, lead, let's find lead. Lead's the second one from the right. And go down to phosphate. All the way down to phosphate, third from the bottom. It's grayed out. This is going to be a solid. Now, what's the ratio? Well, when you have a even and an odd, the best thing to do is cross. 3 here and 2 there. Okay, 3 times 2 plus is 6 plus, and 2 times 3 plus is 6 minus. We got a balanced compound, but it's a solid. Oops, there we go. So that's the precipitate that will form. We know that sodium and nitrate are still in solution because all nitrates are soluble. And most alkali metals are soluble too. Okay, so that's the precipitate. Here we go, here we go, here we go. Yes, yes. Let's see. All right, I went too far. What mass of precipitate will form? Now what we want to do is do the stoichiometry. So for sodium phosphate, we start off with 10 milliliters of concentration of solution that's 0.3 molar. Okay. And lead 2 nitrate is 20 milliliters. And with a concentration of 0.3 molar, 0.3 molar. There we go. That's given. Now, I don't remember saying this, but I'll say it again. Whenever you've got a reaction and you want to find out something elsewhere in the reaction from the given ingredients, you've got to have moles. You can't move anywhere without moles. We can't go there with milliliters. We can't go there with molarity. And previously, we couldn't go there with mass either. You have to have moles. There's a great wall here and here and here. You can't get over it. You can't go under it unless you're a mole. Okay. So we got to find out how many moles here. Remember, molarity times volume. In this case, we're going to have millimoles. So 0.3 times that is 3 point there millimoles, correct? And on this one, we got 6 millimoles, correct? Now, one thing I haven't done yet is balance the equation. Right? Remember how to balance that? Well, if I had done my budget method, I would have taken sodium, phosphate, lead to nitrate here. But the nice thing about these precipitation reactions is they're very well behaved. So we can probably do it without the budget. We can say, okay, I got 3 sodiums here, I need 3 over here. I'll do 3 there. That gives me 3 nitrates. But I've got 6 nitrates. So what if I do like this? Right? Yeah, 6 nitrates. 6 nitrates. That means I need 6 sodiums, 2 times 3. 6 sodiums, 6 nitrates, 6 nitrates. I've got 2 phosphates here, 2 phosphates here. Oops. 3 leads. And maybe I do need my budget.
Well, lead nitrate, shouldn't it be 4.0? Because it's 20 milliliters over 0.2.
Yeah. We'll come back to it. I'm gonna balance the equation first. Yeah, you're right. All right, so let's do it the longhand way. Otherwise, I'm just going to be stumbling around up here. Okay, so let's set up our budget. First of all, did I write the compounds correctly? Yeah, that one's right. 2 here. There, yep. 3 times 2 is 6. Yeah, that's right. And sodium. That's right. Okay, so we got sodium. I'm not going to put the charges. PO4, lead, and nitrate. So we've got 3 here, 1, 1, and 2. And 1 sodium, 2 phosphates, 3 leads, and 1 nitrate. So let's see, we don't have any single elements, so we can't hold anything out. What if we go to we could do like I did before. Now we've got a budget. If I put 3 here, that makes 3 there and 3 nitrates. Okay. Now if I need, let's go to phosphates. I got 2 phosphates there. If I have 2 here, that makes 2 phosphates and 6 sodiums. Okay, so now I need to go to 6 sodiums, which makes 6 nitrates. Okay. Now if I want to get 6 nitrates out of this, I need 3 that group. And that makes 3 leads, 3 leads. Okay, now we're good. Does everybody see that? Oops, I forgot to correct the lid here. There we go. Now we're good. All right. Sometimes it pays to use my own method. Now, why did I bother to do that? Because you can't do stoichiometry with an unbalanced equation. Right? You're either creating or you're destroying matter on board in the formula. We can't do that. Right? So it has to be balanced. Now we can go back and put these in correctly. 10 mils at 0.3 molar, which is 3, correct? 3 millimoles of that compound. And this is 20 and 0.2. 20 milliliters, 0.2 molar is 4 millimoles. Okay. Now, one thing that we didn't cover in class, but I put in the video, was the concept of a limiting reactant. When you're given absolute amounts of two reactants, you can be pretty sure that one of them's going to run out. That's your limiting reactant, and that determines when the reaction stops. So, one way to do that is to say, all right, what if I use up all of this? How much of that will I produce? And then keep this separate. If I use up all of that, how much of it will it produce? And the one that produces the least amount is the limiting one. So if I got 3 millimoles here, millimoles of sodium phosphate, and I want to convert it to lead 2 phosphate, then I want to cancel this one and leave me with this one. Okay, so what are the magic numbers? Coefficients 1 and 2. Okay, so those cancel and leave me with 2 into 3 is 1.5 millimoles of lead 2 phosphate. Now that's only if I use all of this up. What if I use all of that up? Well, in that case, I've got 4 millimoles of, no, not the same thing. Lead nitrate, lead 2 nitrate. There we go. So now I need a way to end up with the same product starting with a different reactant. So what's the ratio here? So this is 1, but that's 3. So this is 3, that's 1. So 3 into 4 is what? 1 1/3, right? 1.33 millimoles of that product. This is your limiting one. It makes the least amount. So now that we have that many millimoles, we want to convert, it says mass of precipitate. What's the mass of precipitate? Well, we can't convert millimoles into mass, right? Because molar mass is in grams per mole. So we have to convert this to moles. So the easiest way to do that is say, what does milli mean? No idea. 10 to the minus 3, right? Okay. So it's actually 1.33. We'll bring this down. 10 to the minus 3 moles. Okay. Now we can convert. What we need is molar mass of the product. So lead is 207.21. 207.21 times 3 of them. And then phosphorus, we have 2, right? 2 phosphorus, which is 3097. And 8 oxygens, which is 16. So I need my calculator for this one. It might be there, but I'm going to do it the hard way. So 207.21 times 3. And then 3097 times 2, and add that together. And then 16 times 8. Add that together. So I get 270 grams per mole. Is that look right? Let's see. We've gotten all of this so far. Okay. And we did that, found out the limiting one. There it is. Then we take the limiting one. And nope. Messed up. That doesn't make any sense. I don't know how I ended up with that one. 207.21 times 3. Yeah, there we go. That in itself is 260. 30.97 times 2, and add that together. And then 16 times 8. Add that together. 811.57. And 54. I get 811.57. So that would go here, 811.57. We're going to be a little bit different than the one and the answer there. Times 133, oops, 1.33 exponent to the minus 3. So I get 108, 1.08 grams of precipitate. Okay. Two places we got the same answer. Everybody see how that's done? Yeah. Just remember, write these things correctly, balance the equation, pick the problem for the information that's given, find the limiting reactant, and then you can determine the outcome. Okay. I only got 2 minutes left, but so I don't have to restart the problem all over again. Let's finish this up. If we have this same problem, we want to know what's the concentration of nitrate ions that are left in solution. Well, the nitrate is a spectator, right? You still got the same moles of nitrate solution that you had to begin with. But is it the same concentration? No, because we added 2 volumes together. We got more volume in there now. So what we need is, what's the moles of nitrate? We've got 4 millimoles of this compound. But how much of it is nitrate? Well, remember, 2 nitrates for every 1. That means we have 8 millimoles of nitrate. What's the final volume in milliliters? Right? Millimoles divided by milliliters will give us our answer. So we got 10 plus 20. We got 30 milliliters. So that would give us our molarity. 8 divided by 30. And 0.27 molar nitrate in solution. Okay. Oh, there it is. Now, this one's a little more difficult. If we want to find out the phosphate ions that are left in solution, look what's happened. This is our limiting reactant here. We're limited by the amount of lead. So we used up all the lead. We used up all the lead, but we didn't use up all the nitrate because this one is excess. If this one is limiting, that means we're going to have some extra phosphate in that solution. Okay? So, how much phosphate did we start with? Well, the ratio is 1 to 1. One of these for every one of those. So we started off with 3 millimoles of phosphate. Right? How much of that did we use? Okay. Let's see. This one. Probably the best way is to look at this right here. 1.33 millimoles is what we ended up with. How much phosphate did we use? 2 times that, This is 1.33 millimoles of the compound. And we ended up on this side with 2.66. 2.66 millimoles used up. All right. So 2.66 was actually used. So what we had left over was 0.33. Three, four millimoles. That's still in solution, in aqueous solution. So now we have that many, and we have the same volume as before, right? 30 milliliters. So if we divide this by 30 milliliters, that should give us our concentration, millimoles per milliliter. Am I losing anybody? I'd be surprised if I were. So this is 1.13 times 10 to the minus 2 molar phosphate in solution. Okay, if we round it off, we put it in standard notation, 2 places, right? 1, 2, right there. So 0.011 is what the problem shows there. All right. So let's see, I'm going to use these. I think they erase quicker. Kind of smudge a little bit, but save time. Let's see. Yeah, we're on to something different now. Now, that was double displacement reactions in nauseating detail. Now we have acid-base reaction. What's an acid-base reaction? Well, we're going to confine ourselves to this type of acid base, which is a Bronsted-Lowry base. And second semester, we get into much more detail. But for now, an acid is a proton donor. That's an acid. A base is a proton acceptor. Okay. Do you believe that's a proton? As long as we're talking about the this isotope. And you strip away an electron, what do you got left? 1 proton. That's hydrogen. That's why we say proton. Now, deuterium and tritium, of course, they have extra neutrons, and that would fit. But they're minuscule parts. We don't have to worry about that. So that's what I mean when I say proton. And for a strong acid, like hydrochloric acid, it is going to completely dissociate into protons and the counter anions, like that. Go all the way. That's a strong acid. If you put a base in solution, it's completely soluble. It's going to produce sodium ions and hydroxyl ions. Okay. If you put those two together, those two solutions, you get an acid-base reaction. And what happens is you got, let's just draw it out. You got this. I'm going to leave the aqueous out first on this side. Plus sodium plus hydroxyl yields what? Well, if it's a double displacement, right? This one swaps and takes on that one, and this one takes on that one. So we get sodium chloride in solution. And we get hydrogen and hydroxyls combining to make water. Okay, so the net equation, since this is aqueous, right? Those are spectators. And the net equation for an acid-base reaction is protons plus hydroxyls yield water. That's why it says what it does. Oh, I gotta start this.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Now, what do we mean by neutral? What we mean is that it's not acidic and it's not basic. Right? I learned early on, like grade school, an acid tastes sour, right? Like sucking on a lemon. I didn't learn till later why. The why is those hydrogen ions. That's what causes the sour taste, the response in your tongue. Whereas sodium hydroxide is a base and they taste bitter. Okay, that's why a lot of the drugs that you take taste bitter, because they're slightly basic. And they put them in some sort of capsule or coating so that you don't excite your taste buds with that bitter taste before you get them in your down your gullet. Okay, so these acid-base reactions, what you have to do is decide, do you have an acid? Do you have a base? Right? If you do have an acid and a base, you can approach it two different ways. You can write out the complete equation and do your balancing and stoichiometry with that equation, or you can reduce it. Once you get that, you can reduce it to this one and put in the values here that you may have to derive from your original, and then you can do the calculations using that one. That's usually simpler. But we need some definitions now. Neutralization. Neutralization is essentially saying that when you put stoichiometric amounts of this and this together, you get that and none of that's left. Now, we're going to learn in the second semester that there is a little bit of this and a little bit of that left over. Okay, but it's still neutral. And if you test the acidity using, you ever use pH paper, litmus paper and that type of stuff, the color tells you it's neutral. Right? There's an equal amount of acid-base character and they've neutralized one another. Well, if that's what you're headed for, if that's what you want to do, you can conduct an experiment called a titration. And a titration essentially takes one known, let's, for argument's sake, let's say the acid is a known concentration. And you add base to it, a known volume of acid, so you know the moles of acid in that container, and you meter out base of an unknown concentration. And when you reach neutrality, by a color indicator usually, you know that you've delivered the same number of moles of base as you have acid. And then you can calculate the concentration of your base. That's a titration. That's one type of titration. In fact, titration field is like, it doesn't have to be acid base. It can be lots of different things. But the equality concept is still the same for any titration. When you reach neutrality, in this case, you're at the equivalence point. When you have equivalent amounts of acid and base from this equation, same number of moles of acid and hydroxyls. That's the exact equivalence point. Now, to do it that way in a titration is very tedious because you have to draw a curve and you have to find out where that equivalence point is. So if you got to do 100, 200, 300 in a day, like I and my technician used to do, you want something that can go quicker. And that's when we use a color indicator. It changes colors when you're very close to that point. So close that the error is insignificant. And that's the end point. So the equivalence point is an actual measured, calculated value. The end point is a color indicator that's close to that value. Has everybody heard about phenolphthalein? Phenolphthalein, it's a color indicator. If the solution is acidic, it's clear. If it flips basic, then it'll turn pink. I don't know if you still can, but you used to get phenolphthalein gum or candies, and you give them to a friend or an enemy, it doesn't matter. And they chew on it and it gives them the runs. Okay. So say we're titrating sulfuric acid with sodium hydroxide. Okay. Here's the difference. With sulfuric acid, which is a strong acid, here, and sodium hydroxide in aqueous solution. I think I better remove some of this. If you're doing a titration with this acid and this base, okay, then you're going to swap. You've got two acidic hydrogens here, but only one hydroxyl here. So you're going to end up with sodium sulfate, which is soluble, and you need two of these because sulfate is a 2- charge. Sodium's a 1+. And you're still going to get water. Okay. But that's not balanced because you have two hydrogens here. And let's see. Two sodiums. Oh, two sodiums. Here we go. Two sodiums. You need two sodiums there. That gives you two hydroxyls and two hydrogens, which makes two waters. So you can do your budget and verify, but that's balanced. Okay. Now you know that if you're given 1 liter of 0.5 molar sulfuric acid, 0.5 molar and 1 liter there, we know that we have 0.5 moles of sulfuric acid. Okay. And how many moles of sodium hydroxide are required? Well, if we have 0.5 moles of sulfuric acid, what's the conversion? Sulfuric is in the numerator, so we put it in the denominator here, and sodium hydroxide here. The ratio is 2 to 1. So you actually need a mole of sodium hydroxide to balance that, to neutralize that acid. Okay, that's where stoichiometry is essential. You need to know what the ratio is. Okay. Okay, that's a quick introduction to acid-base reactions. Second semester, we go into much more detail. But that should be enough to get you through titrations that we would do. Let's see. I think we're going to have one. Calorie 3. Yeah, molecular weight of an acid, lab number 6. We'll do a titration then. Redox reactions. Redox stands for oxidation reduction in chemical terms. Right? Anytime electrons are transferred during a reaction, if you've got electron transfer, you have an oxidation reduction reaction. So you could have a precipitation reaction that is also oxidation reduction. You could have a, which would be a double displacement, or you could have a single displacement where you have an element, say, and you have a compound, and then this A just replaces probably the B. So it would be AC plus B. And that would be a redox reaction, and I'll show you why in just a minute. But anytime you transfer electrons, you have a redox reaction. Oxidation is, well, give me the acronym. Oil rig. Oxidation is loss. So anything that loses electrons is oxidized. Reduction is gain. So anything that gains electrons is reduced. They always occur together. You can't have one without the other. Those electrons have to go someplace. So if they're leaving this one, they're going to end up at this one. Okay. All right. A perfect example of an oxidation reduction reaction is sodium metal plus chlorine gas to make sodium chloride. Solid. Okay. This is neutral. This is neutral. This one has a +1 charge and that one has a -1 charge. Right? So that means sodium had to lose an electron, didn't it, to get that plus charge? So what happens is electrons were transferred. Sodium was oxidized, chlorine was reduced. Now it's not balanced because we have 2 chlorines here and we need 2 there, and that means we need 2 here. Now it's balanced. So I think that's what we're trying to show you here in those pictures. It's an extremely violent exothermic, that is, lots of heat reaction. So this one is oxidized and this one is reduced. Okay. Sometimes it's not that simple. So in order to determine whether what is oxidized and what is reduced, we need some rules. The first rule is in your equation, if you have an element off by itself, its oxidation state, we're using that terminology now, the oxidation state is 0, which is equal to its charge, of course. So 1 is elements, oxidation state 0. Now they could be standalone like sodium, or they could be diatomic like hydrogen, or they could be quadratomic like phosphorus, or octatomic like sulfur. These are all 0 oxidation states. Okay. Oxidation state of an ion is the charge on the ion. So in this case, that would be the oxidation state is +1 for that sodium ion. Now, some of the oxidation states we have to calculate. So we need to this is an accounting scheme. Sometimes it's equal to the charge, sometimes it's not. Because you can use oxidation states for covalently bound compounds where there's no ion. So this is a bookkeeping scheme, so we can track the electron movement. Oxidation state of oxygen compounds in covalent relationships, oxygen would be a 2-, such as water. If we have water, that's a 2-. That means each one of these would have to be a 1+ to balance the oxidation states. Okay. So, and that's the next one, number 4. But oxygens, if they stand alone like this, but if oxygen is like this, you know what that is? Hydrogen peroxide. You know, that's 3% hydrogen peroxide sitting on your medicine cabinet shelf. Okay. Or in the lab, 30% if I want to do some experiments. But 3% is safe. Now these actually bind the 2 oxygens together and the hydrogens out here like this. So this whole thing is a 2-. So each one is 1-. Whenever you have peroxides, the oxidation state for each oxygen is 1-. Now we go to the hydrogens. When the hydrogen is in a covalent compound, it's a +1, like this one right here. Okay. Fluorine is always -1. Fluorine in any compound is -1. For instance, hydrogen fluoride, -1, +1. The sum of the oxidation states has to be equal to 0 for neutral compounds. For polyatomic ions, the sum of the oxidation states must be the charge on the polyatomic. So if we have ammonium like that, we know that the hydrogen is going to be +1 each, so that's +4 total. But we need to keep one of those pluses out for this charge. That means we only have to balance +3. So this is a -3 for a nitrogen. And it's just adding -3 and a +4, you get a +1. So we added them up and we know that we got the right charge. Let's see, did I miss anything? If I did, I'll bring it up later. I think those are all the rules. Occasionally, you end up with a compound like phosphorus pentachloride. We don't have a rule for that one, right? So you have to assume, since chlorine is in the same group as fluorine, we assign chlorine a -1. That means phosphorus is a +5. Okay. I'm way over already. Let me see. How much more we have to do? We got probably a half a dozen slides to go. I guess everybody's okay with staying, right? Okay, that's fine.
Okay.
No problem. We want to do some examples because this is a skill that needs cultivation, determining the oxidation states of elements in compounds. This potassium dichromate, you have 2 options here. If we want to determine the oxidation states, all the alkali, that was left out. All the alkali metals are +1 when they're in ionic compounds. So this is a +1. Oxygen's -2. So if we say 7 times -2, it's -14 total, +2 total. Now, if we put those together, we get a -12. That means that this one has to be a +12 spread between 2. So each one is a +6. Okay, did that go too fast? Okay, the next one is a polyatomic ion, carbonate. We know our rule says that we can give a -2 to each oxygen, which is a -6 total. But we know that we need 2 of those minuses untouched, unneutralized. So we really only need to neutralize a -4. So a +4 here and a -2 here gives us a 2- total. And you can add them up to prove that I'm right. How about MnO2? Well, it's a -2, -4 total. It's neutral, so that has to be a +4. Let's see. Get the animations in here. There we go. And there we go. And there, that's where we are. Oh, I did PCl5 already. Okay. Now, SF4 is easy because we have a rule for fluorine. Fluorine's -1, so a -4 total. Sulfur has to be a +4. That's our bookkeeping scheme. Oxidation reduction, oxidation states. We've already done this one. Except to say that when you lose electrons, you increase the oxidation state. That is, it becomes more positive. Now, it could start off with an oxidation state of -4, and you lose electrons, and you could go up to -1. It's still minus, but you're increasing. You're moving toward the positive. So when you oxidize something, the state increases in value from minus through 0 into positive sometimes. Reduction goes the other way. You decrease the oxidation state when you gain electrons, simply because of the charge balance or the oxidation state balance. All right. Can we determine which one of these is an oxidation reduction and which one is, if any, are not oxidation reduction? The first one is zinc plus 2 zinc solid plus 2 HCl aqueous yields, and this should be aqueous. 2 there. And this will evolve hydrogen gas. Okay. We can do the oxidation states here, like 0, +1, -1, 2 plus, -1, and 0. And we can tell that hydrogen went from a +1 to a 0. Right? So we added an electron to get there. It was reduced. So this was reduced. Chlorine didn't change, so it's a spectator. Zinc went from 0 to +2, so it was oxidized by losing 2 electrons for each zinc. Okay, that's the kosher way to do it. The quick and dirty way is if you have an element on one side of the arrow and you find it in a compound on the other side, you have an oxidation reduction. Guaranteed every time. Or if it's in a compound on this side and it's an element on this side, that's an oxidation reduction reaction, without a doubt. B, let's see, we do them. Yeah, that one. B, if we do the oxidation reductions, oxidation states for each of the elements, we find that nothing changed. Right? I'm trying to save time here. Nothing changed in that reaction. So it's not an oxidation reduction reaction. The last one is a special, actually, I'd want to do this one. 2 CuCl aqueous yields CuCl2. Is that aqueous? Yep. And plus Cu. Okay. See, now we know this one is oxidation reduction. Element here in a compound here. This is a special kind of reaction. Notice we only have one reactant here and we get 2 products. Each of them has copper in it. This one starts off with +1. This one ends up with a 2+, right? Because that's a -1 times 2, that has to balance. And this is a 0. So we've got copper going in 2 different directions. But notice we got 2 of them. So one of the coppers is oxidized and the other one is reduced. Okay. This is called a disproportionation reaction. Disproportionation reaction. It's used in the copper industry a lot for purifying copper. Okay. Now, sometimes when you balance these equations, if you've got an oxidation reduction equation, the most efficient way to balance the equation is to balance the movement of electrons first. And then once you've got those electrons balanced, then you go to the atoms and balance them. So we write the unbalanced equation, we determine oxidation states to see if we do have a redox equation. If we do, then we show the electrons gained and the electrons lost using tie lines. I'll show you an example of that. Then we go to the coefficients to balance the electrons, and sometimes that balances the equation. And other times it gives you a more efficient starting point for the budget. So if we have solid zinc in our example here, and we react it with aqueous hydrochloric acid, and that's going to yield, let's see, I think it's 2. I believe that's right. Let me see. What's the unbalanced equation? Oh, okay. We're going to split it into ions. That's fine. Zinc 2 plus aqueous plus 2 chloride ions aqueous. There we go. What are the oxidation states on each atom? This one's 0. This one's +1, that's -1. That's a 2 plus, that's a 1 minus, and this is 0. So my tie lines would tell me that zinc went from a 0 to a 2 plus. It was oxidized. It had to lose electrons. All right. So we have a loss of 2 electrons per zinc. And then the hydrogen went from a +1 to a 0. It was reduced. So we have a gain of, went from +1 to 0, a gain of 1 electron per hydrogen. Okay. Let's see, I've got animation in here, I think. Yeah, there we go. Those are your values. And then the tie lines. Now we need to balance the number of electrons that moved. If we say, all right, I want 2 electrons to move this way because 2 electrons move that way. Remember, the electrons must balance. Whenever an oxidation occurs, a reduction occurs by the same magnitude. So we need 2 equals 2 electrons. How do we get that? Well, we've got 2 here for each hydrogen, so we need 2 here. Don't we? Okay, that gives us 2 electrons gained, 2 electrons lost, and that may be the balanced equation. Let's finish it off here. Yep. We don't need any more coefficients to balance the equation. Why? Well, we've got the electrons balanced. Let's tally the rest of them. 1 zinc, 1 zinc. 2 hydrogens, 2 hydrogens. 2 chlorines, 2 chlorines. We're balanced. That was an easy one. Okay.